In this video, I hope to give you a short introduction to magnetism. Well, I'm sure at a young age you probably were introduced to the wonderful world of magnets. Maybe you even had the chance to play with a magnet and pick up some pins. You probably learned that magnets have two poles, a north pole and a south pole. And you probably learned that two magnets could either be attractive or repulsive. If you place two like poles, like a north pole and another north pole of two different magnets, or a south pole and a south pole, then the two magnets repelled each other. And so there were repulsive magnetic forces. And then if you took two unlike poles, like a south and a north, then the two magnets actually attracted to one another. These are some of the basic properties that you should know about magnetism, and I hope you learned this before you actually came to this course. There are two poles in a magnet, north and south. But you may not know this, that if you take a magnet and break it up into two pieces, you can't separate the north and south pole. You end up getting two magnets. So you break it up into even smaller fragments, and you still continue to get magnets. You never are ever able to separate the north and south pole. We'll talk a little bit about this property as well. We know that like poles, like a north and a south, will repel each other. And we know that unlike poles, like a north and a south, will attract. This is really similar to what you learned in electricity. To refresh your memory, I put this two little quick pictures to remind you back in chapter 18 when we looked at positive and positive negative charges, and when like charges repel and unlike charges attract. However, do not confuse magnetic poles from electric charges. They are fundamentally different from one another. Let's take a little bit of time to talk just a tiny bit about permanent magnets. Permanent magnets have been known at least since the time of the ancient Greeks. About 2,500 years ago, the Greeks first mined magnetite, which is shown over here in this picture. It's a mineral that attracts iron. The word magnet comes from this magnetite, which was originally mined in this ancient city known as Magnesia. Magnesia is now known as Manisa in western Turkey, but the word magnet is derived from that ancient city where they first discovered these lodestone, as they were called back then, that were able to attract pieces of iron and in fact make the iron become magnetized. Materials that are attracted by permanent magnets include iron, nickel, cobalt, and certain alloys such as steel. These materials are known as ferromagnetic materials. We say that these materials have magnetic properties. Just like you can induce charge polarization on a neutral object, as shown by the image up here, a magnet can also induce a magnetic polarization in the same way. Maybe you've magnetized a paper clip. And you can do this by basically stroking the paper clip always in the same direction across the magnet. And eventually this paper clip will become magnetized and be strong enough to even pick up a few paper clips. Maybe you've done that back in middle school or in elementary school. This process causes the paper clip to become magnetically polarized. You can imagine inside the magnet that there are these tiny elementary particles that behave like magnets. Let's just call them elementary magnets. And when you stroke that paperclip across the magnet, more and more do these little tiny elementary magnets start to align themselves so that there's like a north-south here, and north-south here, and so forth. And when they all lined up like that, then the material has become magnetized. This might help you understand why when you take a magnet like this that has become magnetized and break it into two pieces, splitting that magnet simply just produces two new magnets with again a south and a north and a south and a north, exposing two brand new poles. And so you break this up again. Once again you'll get a south and a north. And you find that you're never able to get these little elementary magnets to break apart. That every time you break that magnet into smaller and smaller fragments, you always end up with a south and a north pole in every little fragment. So this leads to one important difference between magnetic poles and electric charges, and that in spite of extensive research by many scientists, they have never been able to discover a magnetic monopole. No matter what in nature, whenever you break up that magnet into pieces, you always get a north and south. So we say that magnetic fields are due to magnetic dipoles and not magnetic monopoles. And that's mentioned lower down here in the notes over here. In this chapter, we will be exploring the interactions between magnets and introduce the concept of magnetic fields, which is right over here. In class, I likely showed you a simple demonstration where I sprinkled some iron filings over the glass sheet that was placed over a bar magnet here shown in red. So this is an image of what you should have seen in class. And the purpose of this demonstration is to show you what the magnetic field lines look like visually using iron filings. Hopefully you can see how these iron filings will illustrate the direction of the field lines, both the pattern of it, I'm trying to trace out here in blue, along these iron filings, and it also shows you the concentration of these field lines. You can see there's a large concentration here indicating that there is a strong magnetic field there. So this demonstration is great in illustrating the magnetic field lines. But it really only just shows you the pattern. What we really need to do is then look at the direction as well. And so then, the same demonstration, I pulled out some see-through compasses. And the compass shows you the direction of the magnetic field vectors. Here's an animation that I may have showed you in class. Here's a magnet, and this is a little compass that is being deflected. And you can see that it's pointing away from the North Pole. Bring it along to the side here, it's going horizontally over here, and then it points towards the South Pole over here. So if I were to draw on those field lines, which came from the iron filings earlier, you can see that the compass tells you the direction. And so the compass points towards the South Pole and then points away from the North Pole. And these blue lines represent the magnetic field lines. And here's a picture as shown in your notes. It's similar to what I've just shown you. So this is the magnetic field vector labeled as B, and B is the symbol that we use for magnetic field. Moving down to the bottom of the notes, I talk a little bit more about magnetic field lines. And we see that this picture over here kind of gives you a better illustration of what's happening with magnetic field lines. The magnetic field lines outside of a magnet run from north to south, as you can see in this region right in here. But on the inside of the magnet, if you look carefully, you'll notice that it goes from south to north. And this is actually fundamentally different from electric charges, because electric charges basically begin on the north, on a positive test charge and move away from it, and they terminate on a negative charge. Well, that's not what happens with a magnet. They don't actually terminate. They actually go in these completely closed loops. Because remember that there are no magnetic monopoles. You can't simply have just a single North Pole or a single South Pole. They don't exist. Magnets are basically magnetic dipoles. So really, the magnetic field lines really go in a perfect, complete circle. So they go around from the north towards the south on the outside, but inside the magnet they go from the south all the way around back to the north, and it makes this closed loop. Okay, on to the next page, because we probably should talk about the compass and how it works. Well, the Chinese were the first to discover the compass and then use it as a navigational aid. A compass is really a bar magnet. So this little north-south that you see is just a bar magnet that is very easily able to rotate around. So if you want, you could do your own little mini experiment and take a paper clip, metal, rub it against a magnet, get it magnetized, and then just put it on a cork and balance it in the bathtub. You'll find that it always will point in the same orientation. It'll point in the direction of the Earth's magnetic field. And so it'll align itself in that direction. Alternatively, you could just simply take a bar magnet, so just a little bar magnet like this, north and south, and then attach a string to it around the bar magnet, all right, and then just let it rotate freely so that it could rotate around. And again, it will reorient itself so that it will follow in the direction of the Earth's magnetic field. So the compass shows the magnetic field vectors, which are tangent to the magnetic field lines. In the notes, you'll see a diagram of the Earth and the magnetic fields lines that are created around the Earth. The magnetic north-south pole here exists right about here, but this is actually where geographic North Pole is. So it's not actually in the same location, but it's very similar. And so what we see is that the Earth creates its own magnetic field around it. It's as if there's an imaginary bar magnet that's embedded within the Earth. And that near our geographic North Pole is a magnetic south of that magnet. And near our South Pole, geographically, there is a magnetic north. And these poles are not exactly in the same locations, and in fact, they're wandering over time. In fact, if you look down lower in the notes, you'll see that scientists don't clearly understand. It's still under investigation. There's no confirmation of what the theory is that creates the magnetic fields. The main theory right now is that there's a molten iron core in the center of the Earth, and that's what creates the Earth's magnetic field. And we also know, interestingly enough, that these poles will wander, and in fact, they'll periodically reverse every few million years. So if you take a compass and you're standing, say, here near the equator, and you're holding your compass, the compass will basically, the needle will point parallel to the ground, and it'll be pointing towards sort of our magnetic north. But if you move towards the like northern or say southern hemispheres, you'll find that the compass will now start to deflect and have a vertical declination as well, because as you come right over here, then it starts to point straight up and down. Anyhow, let's move on to the last piece here. That's probably the most important discovery, actually, that really leads us into the rest of the chapter, and that was by Hans Christian Ørsted. And this wasn't discovered until, well, that we were able to get electric charges flowing through a wire. So in 1820, Hans Christian Ørsted made a really important connection between electricity and magnetism. He discovered that if you held a compass near a wire, and if it didn't have any current, then the compass just simply pointed in the direction of the Earth's magnetic field. So in this particular case, the Earth's magnetic field might be straight up, and so that's why the compass went this up along the plane of your page, and it went that direction. But if that wire suddenly were to have current running through it, then there would be a magnetic field that would be created around that wire. And if the compass were on top of the wire, suddenly the needle would deflect a little bit to the right. And that's because there would be a magnetic field that is produced by the wire going right, and then the magnetic field produced in this upward direction here by the Earth, and the combination of the Earth's magnetic field and the wire's magnetic field produces a resultant magnetic field that is in this direction. So that led Hans Christian Ørsted to conclude that wires that carry current, or the flow of charge, basically creates its own magnetic field around it. And so there's some mutual interaction between electricity and magnetism. And this important discovery in the 19th century led to many technological breakthroughs, such as electric motors and generators, which we'll discuss in chapter 22.